Okay, so now let's talk about stagnation conditions. These are really, really important. We're going to run into them a lot, so we need to get some good definitions for them. So stagnation, it's also called total conditions, but stagnation or total enthalpy is the following. As a note, it always gets that subscript 0 or subscript naught, and it's simply equal to my enthalpy plus the kinetic energy component. Enthalpy plus the kinetic energy. Now this is for total enthalpy. If I had total temperature, it is similar. It is not exactly the same. We have to rearrange it a little bit. So the H right there is my static enthalpy. That's the ordinary one you're used to. And so this comes really easily from just saying, let's do an energy balance. So if I have, all my energy forms are summed up in here. So I'm saying like no potential energy, no other like electrical charge or anything of that nature. That'd be all my energy. So if I only have two components here, then I see that my enthalpy plus my kinetic energy, that's all of my energy, would have to be equal to my enthalpy at the end plus its kinetic energy. So all of it. And so what this tells me that if I have no heat or work interactions and no change in potential energy, that my total enthalpy will be constant. This is important. This is important because this is actually a measure of how much work you can get out of your flow. When it drops, you have less work you can do. Okay, and so right here, if I'm looking at this control volume going through a nozzle, and we're going to say I'm going subsonically through this nozzle, what I would see is that yes, H.1 and H.2 have to be the same. And hopefully what happens with the nozzle, the velocity increases, which means that my enthalpy would have to decrease, which means that the temperature of the fluid coming out of that nozzle will be lower than the temperature of the fluid entering that nozzle. So it's amazing things that you can already do with this. Okay. So using my total enthalpy as my more or less total energy analog, what I can see is if I take my fluid and I come to a complete stop, so all of that kinetic energy, it just disappears. Well, then I will have all of my energy inside the enthalpy. That's why stagnation points on bodies are really important, because that's where my temperature maximizes, because the fluid is coming to a complete stop. So all my kinetic energy has gone into those internal modes and is now making it very, very hot. Let's see here. So, like I said, when we bring it to a stop, this increases my fluid's temperature and pressure. Why does it increase the pressure as well? Well, it's increasing the temperature of the fluid, and if the density is staying roughly constant, well, it kind of makes sense the pressure would have to go up. And as a note, at this stagnation point, where I have brought it to rest, so let's just say on that tip of that aircraft, someplace else, that is those properties are my stagnation temperature, my pressure, the density. Those are all just called the stagnation properties. Now here's some cool details for all of you. So there's 4 different flows right here: non-adiabatic, adiabatic, non-isentropic, and isentropic. I want to show you what happens for all 4 of these flows. We'll start with non-adiabatic. Non-adiabatic, you really don't know much. Because it's non-adiabatic, you're adding in heat, or heat is leaving the system. That means that your total enthalpy is not constant, and therefore your total temperature is also not constant for a calorically perfect gas, because energy is leaving or exiting. I have to know how much. If I'm adiabatic, well, things get easier, because I'll know that there's no energy leaving my system. It's all stuck in there. And so my total enthalpy is going to be constant. And for a calorically perfect gas, my total temperature will also be constant. Now, how about for non-isentropic? Okay, non-isentropic, but still adiabatic. Okay, so we're going to say adiabatic. Well, this would all be true, but I don't know anything about pressure or density. My total pressure and my total density, nothing happened there. But for an isentropic flow, my total pressure would actually be constant, and my total density would be constant. So both of these things are important. Both of these things are important. And sorry, I want to make one little correction earlier. I said that this was my analog for how much work can get out of the flow. Like, it technically is, but this is a better analog. Because you find out is your energy may stay constant for an adiabatic but non-isentropic flow. However, a lot of it has been dissipated into less useful modes. So If your total pressure stays high, stays close to what it was at the beginning, that's saying that you still have a lot of work you can get out of that flow for whatever you've done to it. Okay, with that little correction aside, thank you all so much for listening, and I'll see you all next time. Have a good one. Bye-bye.